Let's say that r is the rotation matrix of a frame B relative to a frame S. A simple idea is to define the rate of rotation of B, which is also called the angular velocity, to be r dot, the time rate of change of r. But this has 9 variables, and we should be able to find a good representation of angular velocity using only 3 variables. Unlike the curved space of orientations, SO3, represented here as a sphere, at any given orientation, the space of angular velocities is a flat 3-dimensional vector space tangent to SO3 at that orientation. A 3-dimensional vector space can be represented globally, without any singularities, by 3 coordinates. This Tinker Toy coordinate frame represents the body frame B. Now imagine a rotation axis passing through the origin, and the motion of the frame as it rotates about that axis according to the right-hand rule. Any angular velocity can be represented by a rotation axis and the speed of rotation about it. We can express the axis as a unit vector in the S frame, writing it as omega hat S. The hat means that the vector has unit length. We call the rate of rotation theta dot, and we can multiply the unit axis omega hat S by the rate of rotation theta dot to get the angular velocity vector omega S, expressed in the S frame. As the frame rotates about the axis, the B frame x-axis traces out a circle. The linear velocity of the x-axis is in a direction tangent to the circle and is calculated as omega s cross x hat b. A similar relationship holds for the other 2 coordinate axes. Since we will often take the cross product of a vector with another vector, we define a bracket notation that allows us to write x crossed with y as bracket x times y, where bracket x is a 3x3 matrix representation of the 3-vector x. The matrix bracket x is called a skew-symmetric matrix because bracket x is equal to the negative of its transpose. The set of all 3x3 skew-symmetric matrices is called little SO3 due to its relationship to big SO3, the space of rotation matrices. With the bracket notation, we can write the relationship between r dot and the angular velocity omega s as r dot equals bracket omega s times r. The angular velocity vector can be expressed in other frames, not just the S frame. For example, we could write it in the B frame coordinates. Using our change of reference frame subscript cancellation rule from the previous video, we get omega b equals rbs times omega s, or rsb inverse times omega s. R usually indicates the body frame relative to the space frame, so we can drop the subscripts and write the relationship between the body angular velocity and spatial angular velocity as omega b equals r inverse times omega s, and omega s equals r times omega b. We will also find the little SO3 matrix representation of the angular velocity to be useful. In the next video, we will begin to learn how to integrate a constant angular velocity for a given time to find a rotational displacement.